All right. Let's get started with another day of DiffyQ. Coming out in the chat is the link to the live stream that's going on where the high def stuff's playing. So yeah, hopefully you got a chance to see either the fireworks in person or the live stream. Allison makes a note about the noises, and I realize now that those pop sounds and even the big booms, I've heard them for so many years now that like I really should just record them and use them as an ambient sound machine. So instead of white noise, I can just hear people hollering and going, poo, poo, poo. I think I'd get a good night rest with that going on. I don't know what was going on with that bucket of fire at the very end, but I'm on the north side of town and I couldn't see it on the ground, so I saw the live streams or some of the captures later. That honestly looks like a mistake to me, but nothing got burned down, and so that's good. Yeah, that's the biggest bucket of flames I've ever seen. All right, so what do we got going on this week? It's actually a fairly busy week in terms of work to do, but we are entering the phase of the course where we get arithmetic back. The procedures are very straight up, and they mirror other procedures that we've done, and so that's a great thing. And so this week's going to be a lot of practice, but I guarantee you if you practice these things, the outro for the course will be smooth as butter. And so what do we got going on right now? WebAssign number 11 is coming in tonight. Worksheet number 11 is coming in on Wednesday. And then WebAssign number 12, that's coming in on Friday. And then we should spend a little time talking about endgame. That means endgame for the semester for us and endgame for the semester for just in general. So let me talk about those things in just a second. Because right now I just like to bring up the list of things we got to do today. We got to talk about eigenvalues and eigenvectors, really highlight the procedure. We'll look at different examples because we know this comes down to a quadratic equation. And so there are different root types that are there. And then at the end, I'd like to start talking about the relationship this has with ordinary differential equations. Do you know when we'll have our exam grades on Canvas? We thought that we pushed them up to Canvas and unpublished everything on Canvas as well. I'll take a look at that after class today. From what we understood, it was there. All right, so what do I want to do? I want to switch over now to the following diagram, which was given out at the beginning of the semester. So now I'll come in as the, whoa, that talking head of me is huge. Let me chill that out a little bit. There we go. And so what I'd like to highlight is one of the reasons why we developed the grading system that we did is that we weren't even really sure how long we were going to make it in the fall, right? We had no idea that we were going to make it all the way to the fall, through the end of the semester. And so we wanted to set up a situation where you're building up your grade throughout the semester and there's nothing that's looming over your head that could be overly disastrous. And so just as a quick recap on this, right, our grade is made up of multiple different bundles of work. The D-level bundle has written worksheets, recitation attendance, WebAssign quizzes, and we only have one more quiz left. We probably only have one or two more, maybe three tops worksheet a week, and then a WebAssign final exam. Scoring greater than 55% on each of these categories will lead you to a point where you can average them together, and that defines your D-level grade. And then you have the C-level work, which is the WebAssign packets, which are bigger packets of work, but constitute more practice than the C-level practice. And then once you build out of that C-level work, getting a 65% or greater on the WebAssign homework average and an overall average of 65% on the D-level, then we get into the B-level. And we've already done Common Exam 1 and Common Exam 2. So what that means is that if you have a 75% average coming out of the C and D level materials, averaging these two letter grade bundles together, and you scored greater than 75% on the average between those two exams, which was like 99% of the class, you have, assuming you complete the rest of your WebAssign with the drops and maintain your averages and the rest of the D-level stuff, worksheets and final exam, quizzes and attendance, then you have secured yourself a B in the course, and nothing can happen that would take that away. Right? That's the nice thing. There's not like a 30-point huge thing that's sitting over your head looming that threatens you at the end. So if things get hot in other courses and you've got to divide and conquer and split up your time, you can rest assured that you have already earned basically the grade in differential equations, and all that remains is if you want to push it on up to the project level where you're asked to do a project to get your A or A- in the course. And so I bring that up now because we've released, the projects were released on the 7th of April, but we've also now released just today a rubric outlining how we will grade the project components. And so basically the project breaks up into 4 grade categories: just beginning, developing, proficient, and advanced, in a variety of categories that are explained in the announcements that you can take a look at. And we have it set up so that if you're just doing the work proficiently across the categories, that is what will earn you an A. So check out that rubric, start thinking that through. Hopefully you've already at least looked at some of the projects and gotten an aim on what's going on there and where you might like to head. But also remember that if other projects, presentations, final reports, all that's looming over your head, right? If you've secured your B, you can just ride that B on out into the sunset if that's your desire. So that way we can start wrapping things up, which is something we had set up last semester because we didn't know when things would wrap up, right? Cool. Are projects individual? A chat question coming to me. Yes, they are individual. So if you try a project and bomb it, then what that means is that you'll not be given credit for the project, and then you'll just go back to whatever B level grade you had secured prior to doing the project. And then how will you know if you're in contention of bombing the project or doing well on the project? Check out the rubric, and the criteria per category is outlined. Okay. Cool. So that's the lay of the end game land. And then the outro for the course is nice because we just got off that Laplace transform hump, which is a pretty intense hump. And now we're going to mirror a lot of the calculations that we've done before. We're just going to upgrade them in a linear algebra sort of way so that we can think about things geometrically again. And so with that, I'd like to transfer over to the pad. And here is what I've got cooked up on Padland. First page of the notes is always a recap of what's been going down. Right, and a nice little tidy spot where we can go to check out the fundamental results. So where have we been? It's been a while, right? It's been a solid week since we've hung out. So what we want to remember is that our A matrices are going to be 2x2 matrices. And we're going to set them up in this A times X is equal to 0 matrix vector product. If A is a 2x2 matrix, then what this matrix vector product is saying is we have 2 lines in space, and those 2 lines go through the origin. And what we want to ask is, do they intersect at other places than the origin? If the determinant of A is not equal to 0, then the slopes of those 2 lines have been forcibly made different, and then the only spot in space where those 2 lines will touch each other is, in fact, the origin. The only solution to the homogeneous problem would be X is equal to 0, and the columns of this A matrix are linearly independent from one another. And so let me put this in the notes. I said it a lot last hour, and so I should probably just write it down. Linear independence in this case in R2 implies different directions. Right, that's what we have to think. If I'm talking about the columns of the A matrix, if A is a 2x2 matrix, these are vectors in the plane, and if the columns are linearly independent, they point in different directions. So you would be given enough directions to communicate with the whole map. Okay. Then if the determinant is 0, then these lines being discussed about with this matrix equation are the same line, and there are infinitely many points of intersection in addition to the origin because they're the same line. They intersect at all their points. Okay, so that's the basics of the matrices for 2x2s that we need to push forward. And where do we push? We push into something that's called the eigenvalue eigenvector problem. That problem is, given this A matrix, which is 2x2, we seek to find all 2 vectors, all 2 component vectors, and all scalars lambda such that A times X is equal to lambda times X. And what this means is we want to find special directions that, when used as inputs, are scaled to become outputs. So what do I mean by that? I mean, the x goes into the matrix multiplication. That's a direction in space. And then after the matrix multiplication happens, that same direction in space comes out. It could be scaled, but it's the same direction. And so, for instance, if the vector that comes in is I hat so that it points to the east, right? The matrix A multiplies onto this I hat, and if it obeys equation 1, the most that could happen is if you got I hat, maybe you get 2 times I hat, so you go 2 miles east, or you go like 1/2 times I hat, so you go 1/2 mile east, or maybe you go negative I hat, so you go west. But the point is there's this special line in space that is, when put into the matrix multiplication, that line in space comes back out. We want to know that line because it's going to be a phase line. Okay, and then I saw something pop up in chat. Is each line defined by the row or the column? That's the tricky part in linear algebra. The lines in space are defined by the rows, but the columns also define lines in space because they're vectors. We're not going to need to be super astute with keeping them separated. It does get a little muddy in there, keeping those properly separated in your mind, but that's really the goal of a linear algebra course. Well, to solve equation 1, based on some of the talk we had before the exam and then the E-Days break, right? How do we solve this equation? Well, we do a little algebra on this equation, and then we come up with a statement saying this coefficient matrix A minus lambda I, which I'll underline in gray, A minus lambda I, that's the important thing. We set the determinant of that matrix equal to 0. And so how do I calculate the determinant? Well, I do A minus lambda I, which results in the A matrix, only affected by subtracting lambda off the main diagonal. So let me highlight that in yellow. These negative lambdas, where are these negative lambdas coming from? These negative lambdas are coming from this negative lambda times the identity matrix. If that's the case, then where are these A's, B's, C's, and D's coming from? Those are all from the A matrix. Okay. And so we're going to get used to that. We're going to review some more problems today. But when I take this determinant, I do upper left times lower right. So I do A minus lambda times D minus lambda minus the lower left C times the upper right B, right? And so you can write that out. But what I'm going to do is I'm going to write a simplification. If you do a dint more algebra to that result, what you'll find is that lambda squared minus A plus D times lambda plus AD minus BC is the determinant of that matrix where the lambdas have been subtracted off the main diagonal. And so linear algebra says if you want to find this line in space, set this determinant equal to 0 so that you get this clearly defined line in space, not just the origin where 2 different lines intersect. We have this one line in space, and that's what we're looking to find. Okay. So after we process equation 2, what we've really found here are my eigenvalues. And then once we find our eigenvalues, I know this part of the A minus lambda I matrix. And so now, since I know everything that's in this gray A minus lambda I matrix, when it multiplies onto this x vector and is equal to 0, now the game is to find the special line in space. Okay. And those are our key equations for eigenvalues and eigenvector problems. This procedure leads to a quadratic equation. That quadratic equation, as we've seen elsewhere, is going to give 3 different qualitatively different root types. Right? Real different, real repeated, and complex. And so we want to get a handle on how that works out. And then ultimately we want to fold this into differential equations, which is really where we're headed. Okay. So I'm going to fade, and I'll freeze, and I'll get the next slide set up. And then let me know if there are any questions about symbology, language, anything like that. Okay, coming back in 3, 2, 1. This is the problem that we looked at before break. And what we had was this A matrix, and this is how the problem would be phrased. I give you an A matrix, and then I say, hey, find all the eigenvalues and eigenvectors for that matrix. And then you're like, okay, I got this. I'm going to start off with step 1, which is to set the determinant of A minus lambda times I equal to 0. Okay, now let's take another look. Now we've expanded this out. This thing right here that I'm highlighting in yellow, this matrix which is 1, 0, 0, 1, that's my identity matrix. And then lambda is a scalar multiple of that identity matrix. And so how does a scalar affect a matrix? Well, it does the same thing that it would to a vector. This lambda just comes into the matrix and multiplies every element in the matrix. So what that means is that lambda times I only picks up data from the upper left to the lower right, because that lambda hits those zeros elsewhere and nothing happens. Okay? So now, if the A matrix is this 0, 1, 1, 0, then when I subtract away lambda times the identity, what that means is that I come into the matrix, and here highlighted in red will be all the elements from the A matrix. And then here highlighted in yellow will be the elements from the minus lambda I matrix. And so the net effect here is that lambda is subtracted off of the main diagonal, the upper left to lower right diagonal of the A matrix. So if you want to skip out these intermediary steps and just take A and subtract lambda off of the upper left and lower right elements, you're good. Now take the determinant of that. And then when we took the determinant, we get negative lambda times negative lambda, giving me a lambda squared, minus a lower left times upper right, minus a 1. And so what we found out was that lambda squared minus 1 is 0. So my lambdas were either positive or negative 1. Okay? And then what we did was we looked at the case where lambda was equal to negative 1, and we got our associated eigenvector. Now, we didn't get the first eigenvector for when lambda was equal to 1, and so just to, warm up from the past, maybe let's just take this, get rid of it, and try the whole process again, now with lambda 1 being equal to 1. So let's work through that process. What are we going to do? Well, now we're on step 2 of the eigenvalue eigenvector procedure. So I know lambda, I know A, I know the identity matrix, so I know everything inside this coefficient matrix right here. So I write it down. I write A minus lambda 1 times the identity matrix times the x vector is equal to, okay, I have this matrix, which is 2 by 2 right here, and then I have this vector, which is x and y. There's my x vector. And now I just got to populate A minus lambda I. What is A minus lambda I going to have in it? Well, this is A minus lambda I. All I have to do is put in my lambda as being equal to 1. So wherever I see a lambda, I put in the number 1. So I get negative, because there's a negative, I subtract away lambda, and my lambda is 1. And then upper right, I have a 1. Lower left, I have a 1. Lower right, I have a negative 1, so I get a negative lambda, so I have a negative 1. Okay. Now, from this, I get 2 equations. I get negative 1, first row of A, times the first row of the x vector, so I get negative 1 times x, and then a second column of the first row in A, times the second element in the x vector, which is y, so I take the dot product of the first row in A, times the column, and so I get 1 times y, and all of that is 0. I guess I didn't write that, so I'm going to have to move this. What is all this stuff equal to? This stuff is equal to the 0 vector. Okay. And now I do the second row of the A minus lambda I matrix dotted into this column right here. So I get a 1 times an x minus a 1 times a y. So I get an x minus a y is equal to 0. What I want to notice about both of these rows, I didn't actually need to use both of these rows, because what are these rows telling me? They're both telling me that y is equal to x. That's my line in space. Okay? And if I've set the determinant of a minus lambda I to 0, both of these rows should be telling you about that one and only one line in space. And so both rows will tell you about the same line, and for us, that's y equals x. Okay? So now, that doesn't really address the question of the eigenvector, right? We're talking about these lines in space, and it's pretty natural, but what's the eigenvector? An eigenvector is any non-zero vector on this line. Okay. So what that means is that I might choose a different vector on the line than you might choose, that your friend might choose. And so if you're working together, what you have to recognize is that the vector just has to be on the line that's defined. Now, we could all choose different non-zero vectors and we'd all be right. That's totally legit, right? We just tell you about the line by a direction, okay? Because we already know the line goes through the origin. All right. Now here's the big trick. This is the trick that we can get away with because we're dealing with 2x2 matrices. And if you go into a linear algebra course, you will be taught the tools about or that can be used to deal with this for dimension 3 and higher. What we're about to do is super sketchy and will only work in the plane. Okay? So just know that and just be okay with the sketchiness. And here's the sketchiness. What I'm going to say is this is my equation for my line, and I'm going to say let x1 or x be equal to 1. I choose that. You could have chosen something different as long as it wasn't 0. You could have chosen 10. That's fine. Because since I only have two variables, an x and a y, once I choose my x, the equation tells me that my y has to be equal to 1. Once I choose my run, then the equation will tell you your rise, right? And since you only have two variables, the only thing I can define here is rise and run. If you have three variables, there's a third variable that's not defined by the equation, and so you can't use this trick. But what that means for me is that my first eigenvector, which I'll denote with an x1, put a little vector hat on it, is equal to x position, y position, but I've said make x1, and if x is equal to 1, y is equal to 1, and that is my eigenvector. So that's the procedure. Pick up your eigenvalues by solving the determinant of a minus lambda I being set equal to 0. Once you have your eigenvalues, you then return to this homogeneous equation for the eigenvectors. You plug in your eigenvalues. That tells you about an equation in x and y that describes a line in space. You pick an x value, then the y value is picked for you by the equation, and that vector lies on the line y equals x, and that's all an eigenvector is. All right. Questions about that? Yeah, so the question on deck is, what are we going to do with complex values? Benji, the complex value case is exactly the same, but it feels real uncomfortable. So we're going to do an example of real ones next, and then we'll have an imaginary case after that. Okay. For the other eigenvector, would you also have to use x is equal to 1? You can use x is equal to whatever non-zero number you want. I generally choose 1 because 1s are nicer, unless I see fractions coming down the pike and I try to avoid them by a clever choice of x, which we'll see more of when we work more eigenvalue, eigenvector problems. So I'm going to freeze for a second, set up this next slide, and when we get to this slide, what's going to happen is I'll set up the 2-minute timer and have you work through the procedure so that we make sure those steps are under the belt, and then we're moving on to what happens when eyes get into the mix. So coming back in 3, 2, 1. 2-minute timer is up. There's your matrix. Start grinding out those eigenvalues and eigenvectors. All right, 2-minute timer's done. I'm going to start up the problem and we can meet in the middle. Talk about some simplifications that can happen along the way. I want to figure out A minus lambda I. I should now get into the habit of just rewriting the A matrix where from the upper left I subtract a lambda, I leave the upper right the same, the lower left stays the same, and the lower right I subtract a lambda. So I just want to be able to jump right down to that stage right there and be comfortable with that and why that happens. Now I do upper left, which is 3 minus lambda, times lower right, which is negative 7 minus lambda, minus lower left, which is 5, times upper right, which is negative 5. So there's me taking the determinant of that 2 by 2 matrix where lambda is subtracted off the main diagonal. Now I got to get the quadratic equation that comes out of this, so I'm going to put an equal sign here. And the first thing that I want to note is that I will always get a negative lambda times a negative lambda because I'm subtracting lambda away from the main diagonal. So when I get a negative lambda times a negative lambda, what that means for me is I will always pick up a lambda squared, a positive lambda squared. Okay. Now I got to figure out the cross terms, the one that carry the lambdas. I get a negative lambda times a negative 7, so I get a plus 7 lambda. And then I get a negative lambda times a 3, so I get a minus 3 lambda. And then lastly, I have the constant term, which is a 3 times a negative 7, so I get a negative 21. Okay, so those are the 4 terms coming from the foiling of these two quantities, and then I get a minus 5 times negative 5, so I get a plus 25. And so what does this equal? This equals lambda squared. 7 lambda minus 3 lambda gives me a 4 lambda. And then a 25 minus a 21 gives me 4. And then what do you know? I can factor this into lambda plus 2 quantity squared is set equal to 0. So my lambda is equal to negative 2. And that's a repeated root. So what are my expectations at this point? I only have one eigenvalue. So using that one eigenvalue, I'm only going to catch one eigenvector. And so this is a special case where I only get one eigenvalue, one eigenvector. Okay, but it doesn't matter. I'm just working with the data that I have. I found my eigenvalue. So now I go into step 2. And that step is to write down the case. I'm just going to write the case, even though I have one case here. You don't have to do this if you don't want. The case where lambda is equal to negative 2, my only choice, right? And so what do I do with this case? I write down A minus lambda times the identity matrix. All of that is the coefficient matrix times my x vector. And let me plug it in. In the upper left, I have a 3 minus a lambda. But what is my lambda? My lambda is negative 2. So I have 3 minus, to be explicit here, minus 2. And then I have a negative 5. In the upper right, and then a 5 in the lower right, and then a negative 7 minus, again my lambda is negative 2, so I get minus a negative 2, and then all of this times the xy vector. I can simplify this a little more to see what's going on in here. I have a 3 minus a minus 2, so that's a 3 plus a 2, so that's a 5. And then I have a negative 5 in the upper right still, and then I have a 5 in the lower left. And then I have a negative 7 plus a 2, so that gives me a negative 5. There we go. And what do I notice here? I notice that the rows are identical. Since the rows are identical, I'm going to get the expression of the same line if I use either row. The rows won't always be identical, but they will be multiples of one another, right? And if they're multiples of one another, I'll still get the same insight into rise versus run, right? I'm still going to get a line with the same slope. And so, since both rows are identical, I'm just going to pick up this first row, which says 5 times x minus 5 times y is equal to 0. So this is just the statement that y is equal to x. So I'm getting the same eigenvector that I got before. This one's not any more complicated than our previous problems, but the characteristic equation, this polynomial, it was, right? There was more to do there. And so again, I'll just say and then since we don't want to have all of the examples look identical here, why don't I just say let x equal, no, I lie. I'm going to say x equal 1. I need this later on, sorry. But you could choose x equal 10, it's fine. And if x is equal to 1, then y is equal to 1. which tells me my eigenvector, the only eigenvector I can find in this case, is 1 in the first component, 1 in the second component. Okay. Or 10 in the first component, 10 in the second component, pi in the first component, pi in the second component. It's this vector that points to the northeast along the line y equals x. You could also say x is equal to -1. Then y would be -1, and now you'd point southwest. Okay. All of those are legitimate eigenvectors. All right. So those are the two-step process, or that's the two-step process, and this is a repeated root case. Really no different than before. You keep turning that crank. Okay. So I'm going to fade out, I'm going to freeze, and I'm going to get the next slide set up too. What's the significance with the identical rows is being asked in chat. Well, if the rows are identical, the equations of the lines are going to be the same, and that's what you want to see. You want to see the same line being expressed by both rows so that you're getting this line in space where your eigenvectors live on. So another question in chat is, so with a repeated root, you only get one solution. Yeah, there are some strange cases where you actually get infinitely many solutions, but it's so special that I'm not gonna go into it. Most of the time, you can bet dollars to donuts that you're gonna get a repeated root and only one eigenvector coming out of that. Okay, so starting up the next problem, I'm gonna give 2 minutes again. Find your eigenvalues and start working your eigenvectors for this. All right, timer coming down. Let's check in. So you're going to calculate the determinant of a minus lambda I, set that equal to 0, and that is going to be lambda squared plus 1 is equal to 0. Okay? Now, I know that because I've done this problem a lot, or I know that because I can subtract lambda off of this diagonal, and there's really not a lot of data to keep track of, so I could possibly do it in my head and construct this characteristic polynomial, this quadratic equation. But as we move forward, there are some things that might be useful to you that I'll highlight right now. And so I'm going to highlight one in purple and one in red. And so the first thing I'll highlight in red. Oftentimes the capital letter D could be used to represent, also book might use delta. And this is just going to be a placeholder for the determinant of A. And when I look at the determinant of A for this matrix, I do upper left times lower right. So that's a 0 times a 0. And then I go minus lower left times upper right, so minus 1 times negative 1. And at the end of the day, what do I get here? I get the number 1. Okay? That is the determinant of the matrix, something that we've calculated for 2x2s elsewhere. But let me introduce you to something else that happens in matrix calculation called the trace. I'll use a capital T for this. Your book might use tau, right? And it is represented as ter of A. What the trace is the sum of the upper left and lower right elements. So if I wrote it out for a general 2x2, it'd be A plus D, but my little a is 0, and my little d is 0, and so the trace of this matrix is 0. The sum of its diagonal upper left to lower right components is 0. And so I'm going to erase this lambda squared plus 1, even though it's right, and tell you that if you worked this problem and go back to the first slide, you'll see that lambda squared minus the trace of lambda plus the determinant of the A, or minus the trace of the matrix times lambda, plus the determinant of the matrix is another representation of this quadratic. So if you want to start leaning in this direction, if you calculate the trace, which you can do in your head, maybe the determinant in your head or with scratch work, you'll get right down to this quadratic. And so what is my trace? I get lambda squared minus 0 times lambda plus my determinant, which is 1, and that's equal to 0. So I get lambda squared plus 1 is equal to 0. Okay? And so what do I find out here? I find out that lambda 1 is I, and lambda 2 is negative I. Okay? And I'm going to make a little note here. If A has real elements, then if lambda is complex, lambda 1 is complex, lambda 2 is its complex conjugate. So there's a pattern that forms here. If you get a complex number for one eigenvalue in all the problems that we're going to treat in this class, the second eigenvalue is just by definition its complex conjugate. That comes up because of the quadratic equation. But it's going to be a little bit useful in the next part where I now have to take A minus lambda 1 times the identity matrix times the x vector. And so I populate this A minus lambda I times the identity matrix, multiply it by the x vector, and set this bad mamma jamma equal to the 0 vector. Okay. So some notes about populating this matrix. Okay. I'm going to have a 0 from before. And then I'm going to subtract away my lambda 1. Okay. Let me come in here with brown and restate that lambda 1 is really 0 plus 1 times I. Okay? And why would I state that? I want to make the following point uber clear. If you got a more vicious complex number for your eigenvalue, you will get 0 plus I hanging out for that lambda value. And then upper right is going to be a negative 1, lower right's going to be 1, and lower left's going to be 1, lower right's going to be 0 minus 0 plus I. Turns out our eigenvalue was chill, right? And that's cool. But this is the word of caution that I have for you. When you start doling out damage on these complex eigenvalues, the first mistake that people will make is forgetting to surround their eigenvalue with parentheses. That is absolutely necessary because there's this negative hanging out in front of the whole eigenvalue. So it's common for people to not negate all of the eigenvalue at this point. So be on alert for that. Okay. Now, what is this going to be? Well, let me erase the 0 vector really quick and then simplify. My matrix is going to be negative I, negative 1, 1, and negative I. times the x vector is equal to the 0 vector. Okay? So, we had just said in chat, and I had said in lecture, and somebody was commenting in chat, so we're looking for the rows to be the same. And I said, yes, that will be true. Or I mean, not the same, but multiples of each other. They'll be related to the same y equals x equation. But in this case, Sean is asking in chat, shouldn't the lower right be positive I? I don't think so, because I'm subtracting away I right here. I think it should be negative I. And so these rows don't look the same, but check it out. If you multiply the first row by I times I is -1, times another negative is +1. And then if I have -1 times I get this negative I in the second row. So when you get complex roots, it's not always obvious what's going down between the rows. It gets kind of funky. But if you trust your algebra, you move forward to the next step. And what is the next step? I got to figure out this relationship between x and y. So I take the first row and I get a negative I times x minus 1 times y is set equal to 0. And then I'm going to junk that second row. I don't need the second row. I never need the second row, or I never need both of the rows. I only need one of them. I chose the first row. So now I get this equation that y is equal to minus I times x. Okay? That I can be uncomfortable, but don't worry, it's the same game as before. And how did I play that game? I said, hey, let x equal 1. And if x is equal to 1, what is y equal to? Y is equal to minus I. And then my eigenvector for my first eigenvalue is 1 in the x component minus I in the second component. And maybe this gets back to Benji's question about, could I have chosen I for my x value here? And then I get an I times a -1. That's totally legit. Would it be smart to use x is equal to I? I don't know why, but in WebAssign, they choose x to be I sometimes in the videos that they shove you out to. I'm not in general super comfortable with that, just because I think it makes things a little harder. I'm not ever going to do that. I always choose x to be like 1, and the algebraic system in WebAssign should account for that. It should know how to do those scalar multiples to get the eigenvectors to be the same, or to be multiples of one another. So yeah, if that's where the question's coming from, I have seen some reports about WebAssign doing that. I will tend to choose x is equal to 1 because it makes understanding y oftentimes a little easier. Sometimes they'll get complex numbers in there. I shy away from that. It scares me. But it's safe. It's just, it scares me. Note, if lambda 2 is equal to minus I, then A minus lambda 2 times the identity matrix times the x vector. If you go through the work, you're going to find out that instead of a negative I in the upper left, you're going to get a positive I, then a -1, a 1, and then instead of a negative I in the lower right, you'll get a positive I, then you'll get an xy vector right here. And so if you play the same game, what you're going to find out here is that your x2 vector, your second eigenvector, is going to be 1 in the first component, and then not negative I, but positive I in the second component. And so the key point that I'll tell you here is that if your eigenvalues were complex conjugates of one another, your eigenvectors are complex conjugates of one another too. All right. Same procedure, same way to play the game. You just figure out your lambdas. After your lambdas, you set up one of the equations for this line in space. You pick your x value, your y value is told to you, and you do that over all your different eigenvalues. If you have real different roots, you'll get 2 eigenvalues, 2 eigenvectors. If you have a repeated root, you'll get 1 eigenvalue, and 99% of the time, 1 eigenvector. And then if you have complex roots, you'll get complex conjugate eigenvalues and complex conjugate eigenvectors. And that's the lay of the land. Questions? Okay. So I'll freeze that. I'll prep the next screen, and in the next screen, we'll see how this is connected to differential equations. If we tried the other row, it's being asked in chat, if we tried the other row, it would give us the same thing, right? You would get a vector that might look different, but that vector should, if you've done everything correctly, lie on the same line in space. There are infinitely many vectors that lie on that line in space, and so conceivably we could get different looking things, but it's gotta stay on that y equals x equation. All right. So what I've got here, I just pulled down from the previous problem, right? And I've struck out this find all eigenvalues and eigenvectors of this A matrix. We found them already. So now what we're going to say is find a solution to x prime is equal to matrix AX. Okay? So just to tantalize you with where we're going, this is the idea. My x vector is going to be a vector that has an x of t function in it and a y of t function. So it's going to be a vector that holds 2 functions of time. What is that vector going to be? It's going to be the 1, 1 vector times e to the negative 2t. If you go and look at that example, this was the eigenvector. And this negative 2 was the eigenvalue. So it turns out that that eigenvector eigenvalue information is what we will need to build our solutions. What are our solutions? Our solutions are going to be vector valued functions. And they're going to be functions of time. And what do you know? They're going to have exponentials in them. But then sometimes those eigenvalues are going to be complex. So we're really going to get sinusoids and stuff like that. So it's just the same mass spring talk come back again, just from a little bit different perspective. Well, how do I check this? I could check A times X. My A matrix is 3, negative 5, 5, negative 7. My X vector is 1, 1, the eigenvector I found for this matrix, e to the eigenvalue t. So when I perform this matrix product, I do the first row in A onto this vector, so I do a 3 times a 1 minus a 5 times a 2. And so what do I get here? I get a negative 2. And then I do a second row times this vector. So I do a 5 times a 1 minus a 7 times a 1. So I get another negative 2. And so I get negative 2 times e to the negative 2t. I'm just about done. I'll just need a minute more of your time and we'll finish this up. So there's my AX matrix. Well, what's sitting on the right-hand side then is my x prime. So what is my x prime? My x prime is just the derivative of my x vector. And so what is that? That's the derivative with respect to time of the vector. Well, I could have this e to the negative 2t outside the vector because it's a scalar, or I could just bring it into the vector. If I brought it into the vector, I'd have e to the negative 2t times 1 in the first row, e to the negative 2t times 1 in the second row. How do I perform this derivative? I just differentiate the first row, differentiate the second row. But what's the derivative of e to the negative 2t? That's going to be negative 2 e to the negative 2t. And then what's the derivative of this e to the negative 2t? Negative 2 e to the negative 2t. And so is x prime equal to a times x? Well, here's x prime. Here's a times x. And they're the same thing. So why did we care so much about these eigenvalues and eigenvectors? I can use them to build the solutions to these differential equations, and that's where we're headed next. So with that, I will bid you good day, and hope you had a great weekend and enjoyed the fireworks.
Recording stopped.
Have a good day.
Thank you.
Thank you.